Alright, I'm going to talk about separated sets, disconnected sets, and connected sets. And here's a reminder of the definition. It's separated if the closure intersect B is not empty and A intersect the closure B is empty. So these both have to be empty. It's disconnected if it can be written as a union of separated sets, and it's connected if it's not disconnected. Well, let me describe to you what this means. I'm going to give you two examples of sets on the real line, and then I'll move up to higher dimensions where this definition is more important. And over here I'm going to have a green set. Let's say this green stuff represents one of the sets. And over here I'll have a purple set. These sets, if you look at them, there's something different about them. You would want to call this one connected, and you'd want to call this one not connected or disconnected. And so this is the motivation for the definitions of connected and disconnected. We looked and we saw sets like this, we being mathematicians some time ago, and we said we want a way of describing when we have a case where the set looks like this green one versus this purple one. And what we came up with is we said, well, maybe if you can separate them into two subsets such that these don't overlap. In fact, we'll make sure that even if you include the limit points, there are no limit points over here of this one and vice versa. This is the idea of separated. So this set is disconnected, right? So let's label this. This is disconnected. And this is how you should think about it. And this is a connected set. Because no matter how you try to split this one up, try to split that up into there and there, either they're going to overlap or they're going to have to share a limit point. So, I'm coughing like I have something stuck in my throat, sorry. So, in the notation of this would be set A, is this bit right here, and set B would be these three chunks right here. And notice that the intersection is empty, and if you include the closure, if you include that point right there and that point right there, and as well as all these, then they don't even contain, there's no limit point over here for B and no limit point over here for A. That's the basic idea. And in particular, with this closure bit, we want to avoid this situation. So why the closure? Because otherwise what we could do is we could do something kind of stupid like this. And if I want to look at the interval 0, 1 closed, I could split this into A equal 0, 1 half and B equal to 1 half 1. Now notice A intersect B is empty. They don't have any points in common. That one has 1 half. That one doesn't have 1 half. So that's why we need something about the closure. Is because we want to avoid this situation, because here A union B is clearly equal to 0, 1, which is what we want. But if we use A and B here, we don't get this does not describe a separated set, a disconnected set. So we want to make sure that we include some situation like that where if this one doesn't include 1 half and that one does, we want to eliminate that, and we do that exactly by closures. Finally, this is more important in, say, 2 dimensions. In 2 dimensions, you can get sets that look like kind of weird things, like low blobs. Again, this thing is weird, but we want to call that connected. Whereas this set here is also weird, but look, it's got a little bit down here. This is a disconnected set. Why? Well, we should be able to draw, basically we can take this as being our A, and that as being our B, and they have no limit points in between. So we can basically say, separated means it has 2 different pieces, which means it's disconnected. This has 2 different pieces. This has at least 2 different pieces. 1, 2, 3, 4 different pieces. That's what we mean by disconnected. Connected in R are just intervals. Open or closed intervals, or half open, half closed. So it's really easy in R, which is all we're going to need for this class. And I think we'll stop there.